Hello, Chem II, and welcome to your first video of lecture content for the class. We're going to talk a little bit about Chapter 1. I'm going to do Chapter 1 in a series of sections, short videos. Today's is going to be on matter and its classifications and should be a review. It's a really, really awesome way to kind of get your brain flowing back in the mode of chemistry. So let me get rid of my face and move on. What we're going to do today is talk about matter and how to classify it, talking about how to classify all types of matter into mixtures or pure substances or homogeneous or heterogeneous and all that stuff. Again, this is more of a getting your brain thinking in terms of chemistry more than anything else. So Chapter 1 is broken into 3 sections. We're going to break them into sections. We're going to do one video per section. Today is on classification of matter. So chemistry is concerned with 2 things: matter and the interaction that matter has with other things. Matter being the types of substances there are out there, and then how, when they react or when they interact with one another or not, what happens. And energy is a part of that. Whether energy is exchanged or not is a part of it also. It's obviously used in a lot of different disciplines. I will argue that physics is a foundation of all sciences, very, very hardcore, but chemistry is a close second. If you understand the chemistry of substances, you can understand a lot about how things may occur. My degree is in biochemistry. My initial degree is in biochemistry. I really, really enjoy biology and focus a lot on biology and zoology throughout high school and college. But having that foundation of chemistry to understand why things happen made life a lot easier for me, which is one of the reasons why I fell into the category of being a chemistry teacher versus a biology teacher. So section 1 is matter and classification. Let's see if you remember this. So matter is divided into 2 separate categories. There's pure and there's mixtures. Pure is when there's one uniform substance, one uniform material throughout. Mixture is when there are more than one separate identities throughout. In the pure substances category, that's also broken into 2 categories. It's either elements or compounds. How do you know the difference? Well, the elements are the elements directly off the periodic table. There's 118 elements known to man as we speak. 91 of them occur naturally, and you know them as being all the elements on the periodic table. Some are very, very common, some are less so. Some are very, very helpful. Like, for instance, they mentioned lead here. Lead initially was something that was used all over the place because it's a nice, super insanely malleable chemical, worked really well and everything, and then suddenly they realized, whoa, there's toxic nature associated with it. You're going to find a common thread, and I'm sure throughout your studies of chemistry past this class, you're going to find the same thing, that things that are thought to be the be-all, end-all now, later on down the road, you realize, well, maybe if it's not natural, your body doesn't know what to do with it. Sometimes it doesn't. It's not the best thing in the world. So always show a degree of extreme caution when revolving around use of chemicals. You treat them all as if they're toxic or dangerous. That's a safe way to go. So compounds are the other side. That's where you have a pure substance, but they're a combination of 2 or more elements. Now, the combination here is a chemical combination. There has to be a chemical bond holding those elements together. For instance, methane is listed here, is CH4. It's 1 carbon atom chemically bonded to 4 other hydrogen atoms, and they're always in the same proportions. H2O is always hydrogen, 2 atoms of hydrogen with 1 atom of oxygen, never varies 2 to 1 ratio. That's that fixed composition. But water, H2O, is H2O and H2O and an H2O molecule and H2O, all the same. That makes it a compound, not a mixture. So pure substances can be divided into elements or compounds. Is it 1 element off the periodic table, or is it 2 or more elements off the periodic table chemically combined together? What about the mixture side? Well, they talk about the composition. Again, the composition of the molecules, we talked about that, it is fixed. They talk about how they come together. And honestly, one of the things that's kind of most neat about compounds is they very rarely have the same chemical and physical characteristics of the elements they were combined from. So, for instance, sodium is a metallic, very, very soft element. You put it in contact with water, it explodes. Chlorine is a gas that is toxic. You breathe it, you could die. Yet when you put them together, you make table salt. And table salt is that wonderful stuff that you put on your French fries. So obviously, a flammable metal and a toxic gas being brought together to make something that makes your French fries tasty. You can see that there's a dramatic difference in the chemical characteristics. So elements, compounds. Now we have the mixtures. So the mixtures, that's when you have two or more substances are combined together, but they are not chemically combined. They're not chemically combined. They just happen to be in the same space. So the example that I'm going to show you on the next slide is copper sulfate and sand. So take copper sulfate, which is blue rock, and you mix it with sand, the two will retain their original chemical characteristics. Whereas sodium chloride, the table salt, you don't have sodium characteristics and chlorine characteristics in that combination. So here's a picture of copper sulfate and sand. You can definitely see the blue pieces. You can definitely see the brownish pieces. And if you were to take this material and dissolve it in water, the copper sulfate would dissolve and the sand would not, because copper sulfate is soluble in water and sand is not. So they retain their chemical characteristics. They do not combine to make one substance. In regard to mixtures, there's two types. There's homogeneous and heterogeneous. Homogeneous are the ones that are uniform in consistency. You really can't see the differences. The example they give here is seawater. If I were to take a glass of seawater, shy of maybe having a little critter floating around in it, or maybe it's super toxic, it's not going to seem, you're not going to be able to see the salt molecules and be able to see the water molecules. However, if I were to boil that seawater, sooner or later it'd get to a consistency where the salt would start crystallizing out. You know the chemical characteristics are there. They are separate. You just have to separate them out through physical means. That was something you talked about in Chem 1 a lot. Another term for a homogeneous mixture is a solution, and we'll talk about that in a second. On the heterogeneous side are the ones that are non-uniform. The example they give here is rocks. I always say chocolate chip cookies, or mint chocolate chip ice cream, or Rocky Road ice cream, or pizza. You can see the parts. You can see the pieces. There's definitely distinctively different components there, all in one entity. It's a mixture. So mixtures can be divided into heterogeneous, which means you can see the differences, you can see the separated parts, and homogeneous. But the big difference between mixtures and compounds are mixtures are combined physically and compounds are combined chemically. There's a bond there. So here's an example of two mixtures. The one on the left is homogeneous. That looks like it's brass or bronze. It's just a mixture of copper and zinc combined together. A big slug. You can't really see the copper molecules. You can't see the zinc molecules. But if you were to put this material into acid, the zinc molecules would react with the acid where the copper molecules would not. What about the one on the right? That's an example of granite. Granite is you can see the little different graining and the different colorations. That's going to be a heterogeneous mixture. So the last thing to talk about is, what about that homogeneous mixtures and the differentiation there? Well, first off, they already said in an earlier slide that homogeneous mixtures can be referred to as solutions. A solution is when you mix together one thing and another thing dissolves it. The classic example that I always use is Kool-Aid. When you make Kool-Aid or some liquid beverage, you take the flavors and the sugar and you dissolve it into water. Water is the solvent. That's the thing that's doing the dissolving. The solute is the thing that's being dissolved. And you can dissolve solid, like you dissolve sugar into water, or you can dissolve gas, like as in soda, Coca-Cola, or Pepsi, have gas bubbles dissolved in it to make it all fizzy. You've got one part, which is a larger amount. Water is a larger amount of Kool-Aid or any beverage. And then all the other flavors and such are the smaller amounts. Those are the solutes. So you can divide heterogeneous into nothing, but homogeneous into solutions, or there's a special category of homogeneous, which is kind of a in between heterogeneous and homogeneous. And that would be what's called a colloid. A colloid is somewhere very, very fine line between a heterogeneous or a suspension and a solution, because you've got in a colloidal suspension, which is what it's called when you have a colloidal suspension, a colloid, you have particles that are so small that they float and they are suspended in the solution, but you can't really see them. They have what's called the Tyndall effect. It's a fancy word for the ability, if you shine a light through it, that the particles are floating around and you can see the particles reflecting off of the light reflecting off the particles. So for instance, the example that I always use as a way to describe this is fog. If you've ever driven or been in a car while your family has driven in fog, you realize the headlights, you can see the beam. Or better yet, if you're ever out camping and you played with a flashlight, say in a campfire, you can see through the smoke. You can see the beam of light going through that smoke. That's a Tyndall effect. That's telling you that smoke, which is a good example, that smoke has built into it a bunch of small particles that, given the time, they'll fall and settle out, but for a while they're stuck in solution. The one that's classically used from a chemistry perspective, and your textbook talks about milk. Milk is a colloidal suspension. You actually have a bunch of fat particles floating around in milk, and they stay in suspension for a very, very long time. Do they settle out sooner or later? You put it in a centrifuge and spin it out, you can get them to fall down to the bottom. But there's little fat molecules floating around in the milk. So that's called the Tyndall effect. And the particles are of different phases. The examples they give are smoke, air, and dairy products. And you can see here in the vision, the one on the left-hand side with the picture on the left, the vessel on the left of the two is a solution. The vessel on the right is a colloid, because as you shine the light through the two, you can't actually see the beam in the liquid on the left, but on the right, you can. Same thing on the far right-hand picture. It's a little foggier. But the one on the left, you can't see the beam go through, but you can actually see the beam going through the colloid on the right-hand side. So that's the separator between the two. So if you look at this, matter can be divided into a multitude of different categories: pure or mixture. Pure substances are either elements or compounds. Mixtures are either heterogeneous or homogeneous. And homogeneous can be separated even further, one step further, into being either solutions or colloids. Let's see whether you got this. So gold. Where does gold fall in the category? Well, gold is on the periodic table. So it is a pure substance. And is a pure substance, it is an element on the periodic table. What about gasoline? What do you know about gasoline? Well, gasoline is actually a mixture. Gasoline is a mixture of a whole bunch of compounds, but because you can't see the particles, it's a homogeneous mixture. In this case, it would show no Tyndall effect and is a solution. Now, the next two are kind of tricky. Pure water. Pure water is a compound. It's H2O. But tap water, the stuff you drink, has a bunch of other stuff in it that maybe you are aware of. You've heard of hard water. Might have other things floating around in it that you consume. So it's a solution. Milk, we already mentioned, is a colloid, so it's a mixture. It's a homogeneous mixture, but it falls under the category of colloid. Dairy products tend to do that because of the fat. Brass. Well, brass, we saw in a previous example. Brass is a mixture. It is a homogeneous mixture because you can't see the different particles, and it is a solution. Kind of a weird solution. It's a solid solution. Apple pie, yum. Apple pie. Well, apple pie is a mixture. It's a heterogeneous mixture. You can see the particles. You can see the apple pieces, and maybe your parents put in other things in their nuts or raisins or whatever. I don't know. Everybody does different things with their apple pie, but it's definitely heterogeneous in nature. And then finally, Mountain Dew. Mountain Dew is a homogeneous mixture. You can't really see the particles, but you know in there's caffeine molecules and there's sugar molecules, and there's flavor molecules. There's all kinds of weird stuff in there floating around in that water. So how'd you do? Did you get those? Did you get the idea of what the different categories are for each one of the different components? So let me bring my face back up. Sorry, I got away from this. So that wraps up the section on matter and classification of matter. Hopefully it was a bit of a refresher. Next time we're going to have a lecture on the category section 1.2, a little bit more of just getting you used to thinking in terms of chemistry before we dive into the real content of Chem 2. Until then, have a good day. I will see you in class in our synchronous time. Toodles.